So my name is Filip Hahs, and I'm an undergraduate student at the Warsaw University of Technology. And I will be talking about PyWrapper workflows for non-standard applications. Yeah, so just a quick introduction of what Pedro said. The PyWrapper is a set of Python bindings for the C++ code. And what it does, it enables fast implementation of non-standard workflows. It's very flexible, since you can run simulations which are not permitted by the configuration file. And you can also integrate with external libraries easily, which will be demonstrated in my work. So the first application, which I have used the PyWrapper for, is implementation of optimal checkpointing. I know Pedro said that it's impossible, but I think I got it working. Maybe I have to investigate further. So the idea is that when you're doing discrete algebra calculations, you need to save all the time steps. However, this can take up a lot of memory. So the solution to this is to save only some of the time steps and then recalculate the solution from the closest available checkpoint. Closest available time step, which was called the checkpoint. So there are, of course, multiple ways to figure out which time steps to save. And there are two sort of major ones which I focused on. The original one by Mr. Greenbank, where this idea is sort of introduced, and logarithmic growth of complexity is achieved, so that depending on how many, as you increase the number of time steps you want to calculate, the number of recalculations grows only logarithmically. And yeah, and on this article, Mr. Kwikwi and a few other people built and wrote this article where this is expanded to online checkpointing, where the number of checkpoints does not have to be previously known. So let's take a look here at what one of these checkpointing schedules look like. Let me restart it here. There's some. So we start here with just the first time step being calculated, and we have 6 checkpoints available, and we need 40 time steps. So as we continue, yeah, time steps are being forgotten. In the past here, you can see that they disappear as the direct solver continues, and then now we go to the adjoint part, and they're restarted from the previous last remember checkpoint. Yeah, so let's show maybe how many times we have to recalculate. So as you can see here, in my implementation, I have achieved this logarithmic growth. Depending on how many checkpoints we have available, the number of recalculations grows. However, not so quickly, especially when we have many time steps available. This growth is not that fast. Yeah. So now I'll move to the second application of the PyWrapper, which I have come up with, is the use of principal component analysis for memory, for reduction of required memory. So principal component analysis is when you have sort of some random variables, it captures the axes in which most of the variance is preserved. Yeah. So the main idea is to use this technique instead of checkpointing. And in the library scikit-learn, there's the incremental principal component analysis, where the amount of memory required is constant and is equal to the number of principal components we want to store. And what is interesting is there is sort of a one-to-one correspondence with storing one of these principal components and one checkpoint. Yeah, and then of course we would use this unreduced flow field for adjoint calculations and maybe some other purposes like visualization, maybe some reduced order modeling. So here I have examples of these principal components. This is flow around a cylinder. Viscous uncompressible flow. And you can see six modes, 6 of the first modes which carry the most variance. You can see the sort of the vortices behind here being resolved. Yeah, and so the idea of how to do this is to first run the mode identification or the component identification, and this is done in batches of time steps. So the algorithm in scikit-learn requires batches of time steps. So we do 10 time steps, and then we run the algorithm, which finds the modes, and then we delete them, and we run another 10, and the mode identification is refined. And after that is complete, we restart the simulation and then create a reduced model from the start, one time step at a time. And then we have our model. And so how much error is created? Here we have the mean error across the domain, depending on how many modes we use. So as you can see, as the number of modes saved increases, the precision also increases, however, up to a certain point, after which we sort of have a case of diminishing returns, and we probably don't want to save this many modes. So we can see this is quite accurate. I calculated the error for one flow variable. Yeah, and it's averaged over a certain period. Yeah, and this is how it's defined. Here I have some articles relating to this problem. The final application is flow control with discrete adjoint. And the problem is to reduce drag on a 2D cylinder placed in incompressible viscous flow by rotating the cylinder by setting the moving wall velocity with the PyWrapper. Yeah, and I used a simple gradient descent, since that's all I could get working. And I also must admit that I selected a Reynolds number accidentally, which is too high, 2000. Hindsight is 2020, but it's definitely too high. And I optimized time steps from 400 to 600. Yeah, so the general idea was to start and create an initial control vector, calculate the direct problem while changing the rotational velocity, calculate the discrete adjoint problem, remembering to reverse the control vector when calculating the discrete adjoint, and then get the sensitivities from the history file and update the control vector. For this problem, I did implement the sensitivity calculation versus the moving wall velocity. So there are many problems with this approach. Firstly is that it appears that this direct solver only finds instantaneous sensitivity, which is not optimal. It's not really correct. Yeah, and the computational cost is very high. And despite these problems, I have achieved a result. And that is a reduction of 15% of the average drag over around 65 optimization iterations, after which it stopped optimizing. Yeah, so here we can see some more graphically pretty results. In the first graph here, we have the drag. On this axis, we have the time steps, and here we have the drag coefficient as the color, and the optimization iteration is the y-axis. Here, there was sort of a breakthrough, and the average drag fell dramatically. This is the result I achieved, and afterwards, also here in the control vector, which is the rotational velocity, there were some oscillations formed. After which I stopped the optimization process and called it a day. Basically, yeah. So I'll finish off by showing this optimized flow. Here at the very end, we can see that the vortices stop forming and sort of one big one, and then there aren't any vortices being shed, and this is sort of the mechanism of the drag reduction. Here's the control vector as it was calculated for the final iteration. Yeah. So here's some literature, including an article by Professor Gauger. Yeah. In the future, I plan to sort of combine these for my final thesis. Actually, I plan on combining, especially the principal component analysis with the optimization of the drag on the cylinder problem with this one, to see how the accuracy of the model reduction impacts the sensitivity calculation. Okay, and I would like to thank my dean for financing my trip here, Professor Jacek Szymbarski, for guiding me, and Dr. Pedro Gomez and Toby Kaplan for helping me do this. Without him, this wouldn't be possible. Thank you for your attention.
this amazing result, especially considering you're only, well, let's say you're not a PhD student yet.
No.
So usually these kind of results are presented by PhD students. So any questions for Filip?
Yes.
Yeah.
Just for curiosity, the rotation velocity again. Do you see, because in traditional we just resist the natural working shedding, do you maybe see, if you look at the rotational velocity, does it resemble in its period, amplitude, or in its period, the shedding, like if you look at the drag of a fixed cylinder, and then the rotational velocity, does it maybe add up, or does it maybe look very?
So the question is, as I understand it, does this resemble the drag on the uncontrolled flow?
Yeah.
Okay, so let me just so no, it does not. Sort of what I've noticed is that the mechanism of drag reduction has to do with the increasing of the period of the vortex shedding. So as the drag falls, the vortices get shed less and less, and because of this, it doesn't really. I haven't noticed really much of a correlation between. Although this is, like I said, this is for a Reynolds number which was too high. Now I'm calculating one with a lower Reynolds number, and there is some more similarity. Yeah.
Yeah, Toby, another question?
Any chance to exit the PCA on something which is not, let's say, or which doesn't have periodic nature to it? So I know that for forced motion, like if you pitch a wing, actually, or if you have the periodic shedding cycles, that works very well. Any chance you get a test of something more favorable that more? Yes.
So the question was whether or not I tested the PCA on flow which isn't quasi-stationary, and the answer is unfortunately no. No, I haven't done that. I have a little bit, I'd say, limited computing resources here, and yeah, I haven't done this yet. I know this probably wouldn't work as well, and the result wouldn't be as nice as it was here. Yeah, but I haven't tested it.
Hello.
Thank you very much for the presentation. So I understand, right, you have applied the PCA to reduce the solution space. Use that for joint solution, right?
Yeah, to unreduce it for a joint
So
solution.
my question would be, probably a bit beyond this work, is there any key that this reduced solution can guarantee the solution of your joint?
So the question is whether or not reducing the flow field from the PCA guarantees a solution for the adjunct problem, and the answer is I don't know, but I will find out. This will be part of my final thesis, is examining this problem.
To that, I guess, you basically do not solve your equations anymore when you unreduce. So if your fixed point in each answer is not valid, then the actual good, then it's a matter of how good the adjoint solver work with not so fixed point-ish fixed points.
Yeah, so you have a lot of bank and your consideration to the solution will be more and more accurate. So maybe the question is how many ranks you need to guarantee a solution for convergence.
Yeah. That's
All right. Other questions for Filip? Yeah, Toby, one more question.
Or was it more implementing this then for online checkpoint? you have limited resources, but often on passwords you can not
Okay, so the question was, did I have any need for checkpointing? And the answer is no. Some ways you could call this a gateway drug to other PyWrapper applications. Yeah. So this is how I started the first thing I did with the PyWrapper was this.
All right. Other questions? No? If not, then thanks, Filip.